Okay, so now we're going to move on to the part 2 of the actual implementation of the PLP package. So I'm going to begin talking about what goes into the PLP package and what comes out of the PLP package. Hopefully we'll be able to get it done before lunch. If not, we might just go through point 2, what goes in, I'll do what comes out after lunch, because I'm guessing everyone's quite hungry now. So we're going to do this for an example of actually reproducing the CHADS2 using our data, just using the 5 variables. So we're specifying our problem. In people who have atrial fibrillation, can we predict ischemic stroke during 0 to 1,000 days after they have the atrial fibrillation diagnosed or recorded in the data? The predictors, we're going to use the 5 predictors that the CHADS2 uses. So we're going to see how well we can reproduce their model in our data. So you have 2 options now. Those of you who know Atlas, it's an interface where you can create cohorts, concept sets, and it also has now the ability to generate the R code for prediction. So I'm going to show you that example. If you like R, you can actually do everything with R yourself, and there's manuals on that in the GitHub, so you can actually test that, and you'll be able to see the R code that's generated and see how the inputs are affected from what you actually want to do for the study design. So the next few slides are going to be on the Atlas. So what is Atlas? I know many of you haven't used Atlas. We did the survey, and a lot of people said they haven't actually had experience of Atlas. It's what we use a lot in Odyssey to create our cohorts, look at our vocabulary, create our concept sets, and so on. So the first thing you need to do when you're doing a prediction model is specify your T and your O. So these are creating 2 cohorts. So if you're in Atlas, and you can actually view Atlas now if you've got your computer open by going to odyssey.org/web/atlas/#sign/home, and this will give you your Atlas. In the next presentation I'll actually be running through this, and I encourage you to run through as I'm going through it. Right now, it'd be good if you're just going to have a look at what's on the screen so you can see the options and how to actually create things. So if you go to the cohort in this area here, if you click on that, it will then enable you to create a cohort. So I've got the link there for you highlighted more, because I'm sure no one can actually read the small print. So the top one, first step is to actually create the cohort. So if you click on that cohort button, you get this page come up. And you'll have a list of any cohorts that people have already created. So depending on the connection you've got, then this might be empty. In the odyssey.org, this has got a few cohorts created, and you can actually click on them and have a look and copy and start them as a foundation if you're creating a cohort. Otherwise, you can say create a new cohort here, and you click onto that button, and this will take you into the ability to create the cohort. So the first thing is that you can actually define the cohort you're creating, so you can give it a name, and you can press save here to actually then add it, and that will get then added to that table you just saw in the last slide. And then you've got the inclusion-exclusion criteria. So these are the rules of your cohort. This is the primary rule up here, and then you can kind of go down and add in some further inclusion criteria. Now, one thing that you'll see is that you actually have a condition of a certain event or a drug of a certain drug, and these are actually concept sets. So you can define that by going to your concept set, or the concept up here somewhere. And then you can generate, First is just talking about the generation. So if you go to the generation tab, you can then generate and create your cohorts into a table, but you have to do it for each database you've got set up. And you do the same for the cohort. But yes, if you want to do the concept set, then you go to this concept here, and this will then take you into a table again where you've got concept sets that already exist. And if you want to create a new one, you go up to your new concept set. You can then give that a name, and then start going to the vocabulary to add things. So the way you can add in the vocabulary is that you have this shopping cart. So you can type something into the vocabulary, so anything you can put in stroke, and you'll get a lot of concepts that come that contain stroke in their name. And then if you want to add any of the concepts, you just go to the shopping basket. It goes orange if it's added. And if you want to get rid of it, you click on any orange, it will kind of stop, it will go back to the grey, and that means it's out of your concept set. So that's how you create the concepts. They're used for the cohorts. Once you create your cohorts, the next step is the prediction. So this is a new feature that's added into Atlas recently. And if you go to if you open Atlas now, you'll see this prediction button here. If you click onto that, you end up with a similar design. You get your table of any existing prediction models, or you can go to a new prediction model here. If you click on the new prediction model, similar process, you can name it here, so whatever name you want to give. It might be, for example, PLP training T, and then you can save. And then you need to specify your T and your O. So these are the T and O's that you've created previously as concepts, as cohorts. So if you go to this little button here of the folder, this will give you the option to actually pick any of the cohorts you've created already and add that in. So for example, I've added in a training cohort for atrial fibrillation for the CHADS 2, and I've also added an outcome of the stroke. You can then select any model that you want to use out of the ones we've actually got pre-built. So you've got the lasso digit regression, KNN, any of the tree-based methods, AdaBoost. You go and select those. Once you've selected, for example, the random forest, it then pops up with all the hyperparameters that you can put in. So then these are the default settings for the hyperparameters. You've got a default setting of a depth of 17. The number of variables is the square root of the total number of variables. So that's the number of variables you put in each model. You have number of trees to build for each forest is 10 or 500. And it's going to do a variable importance first to pick out the important variables. So it looks at every combination of those, and this is the hyperparameter grid that it's going to go through when you're doing your cross-validation to pick out the best one. If you wanted to add in some more parameters, you can put in the values separated by a comma here. So you could put 7, 2, 4. And it will look at trees that have a depth of 17, 2, and 4. So this is actually what the grid search looks like. So for everything that you put in, these are the hyperparameters. Depending for everything you put in, you'll get a setting for every combination. So if you put 17 minus 1, you had trees 10, 500, 10,000, and 1,000, and true, then you'd end up with all of these settings being searched for in your cross-validation. And the setting that resulted in the best performance would be the one that would end up being chosen for the final model. For the lasso digit regression, again, if you put that in, it will change the parameters settings here, and you can put in the values. Again, this will do a search for, so this is the multi-layer perception. For the multi-layer perception, for neural network, you've got 2 parameters, regularization, hidden nodes. So again, you can put in the values, and for every combination, it will do a search and pick out the best ones for you. It is worth noting that the bigger your grid, the slower your training is going to be, because you're doing n-fold cross-validation for every setting, every combination. So if you put in 50 values for L2, 50 values for number of hidden nodes, you're going to have a long wait for it to actually train. Once you've defined your model and you've put in your hyperparameters, so define the grid search, you then need to put in your time at risk. So in the Atlas, you can only do this relative to your cohort start date for your target population. But if you were manually editing and using R, you've got a bit more flexibility on that. But in this model for the CHADS, we're going to look at 0 to 1,000 days from your cohort start. So we put in 0, and in this case, actually, we put 0 to 365. So this is looking at 0 to 365. In the actual code online, though, you actually see it's 1,000, because when we're reproducing the CHADS 2. And then you need to generally specify a minimum look-back period. So this is the minimum observation everyone needs to be included into the model. If you've got someone who was into the cohort, but they've only got 10 days of prior observation, they're not going to be very useful, because you're going to be limited for the variables that you're constructing for them. So generally, as a good practice, we're saying that we want people to have about a year's worth of history to be included, just that we have variables for them. You can actually do some exclusion. So this is a question that was actually asked earlier about the competing risks. What do you do if you have someone who's only observed for part of the time at risk? Do you get rid of them still? Do you include them? You have an option. You can either say, I want to include people who are partially observed for the time at risk, and just assume that if they don't have it by the time they were left, they don't have it, which is going to add some noise. Or you can say, I want to get rid of them, and say if they're only partially observed, we get rid of them, except if they have the outcome, because you know they've had the outcome by the time they've been removed. So you have these different options for different settings, and I would recommend that if you think there is a competing risk, for example, you're looking at an outcome that might be affected by death, then you might want to try doing all the different settings you can. So, okay, let's include everyone, even if they were removed before the full time at risk. Let's remove people who only had partial outcome and see how stable your model is, and see if you get a similar model for the different settings. Then you have the option, because when you're creating the cohorts, you don't necessarily have to have distinct people. You can actually have people at multiple different time periods, so they'd have different T1s, T0, sorry. So in this case, you might say you only want to use someone first for the first time. So if you've got someone who has a repeat exposure to a drug and you're doing the prediction from the exposure time of that drug, you can say, actually, now I only want to restrict them to the first time they take that drug. And again, it might be when you're doing the prediction, this is something that you want to actually investigate what the effect has. So you can actually put that as yes and put that as no and see what the effect is.
I know there's a mic on the table somewhere, which is making the first exposure, is it decided by the data condition error table or by the condition current?
So the first exposure here will be when you've extracted the data. You'll have for each person in the target population, you have their start date, cohort start date, and the first exposure will just say I'm taking the first date once you've extracted the data. When you're defining the cohort, you can actually define the date that you want. So it depends on your cohort definition.
Yes, but I mean, there's this message. So let's say it's going to be the age fit in this case, or it's going to be the stroke.
Oh, so in this case, so it's always relative to the target population start date. So T0 is always the target population start date, which will be the AFib. So this will be, in this case, if you said yes, this will be the first time in their target population they had the atrial fibrillation. Now, sometimes when you're creating the cohorts, with the big data we have, you can actually have target populations that consist of millions of people. So when you're extracting the data, it can take actually a couple of hours or more, depending on the computer you have and the setup you have. So we've added in here an ability to actually sample from the target population. So it might be that if you're trying to do some preliminary study, you just want to say, okay, is my model is this prediction likely to work before I invest too much time trying to tune it and so on. Maybe I just want to extract a sample of the data, the target population, train the model and see if it's an error in the curve of 0.5 or an error in the curve that's 8.8 and gives you a bit of promise that you might be able to get something good out of it. So here you can actually sample, and the default setting is 10,000 people. This is just to make it very quick, and you can turn that off if you want. If you wanted to use everyone in your data and you weren't in a rush, you can turn that off, or you can increase the sample size. It's pseudo-random at the moment, and the people that get sampled. And then you have the option as well of whether you want to remove people with the prior outcome. So this can be defined when you're creating the cohort, or it can be defined after. So again, if you're doing some sort of sensitivity of the model and you want to say, well, what's the effect? How does the model performance drop down if I remove people who've had the outcome before T0? Then you can look at investigating this and try different models with different settings. So this is just saying that we're going to remove people if they had the outcome prior to T0, and we look back 99,999 days, so pretty much their whole prior observation. But you could just say, I want to remove anyone who has the observation in the last 30 days and the last 365 days and so on. So you can change this value here to how far you look back. Then you have the settings for you actually doing your test train split. So the default at the moment is your time split, but you can change that to person as well. So if you're doing a time split, it basically will say, okay, with the percentage of data, if it's set as 25 as it is here, you look back in time and you say, okay, what time point were 25% of the people observed after and 75% of people were observed before? And then you say, okay, the older 75% of data will be used to train the model, and I'm going to validate it on the last 25% of the data. So you can see then if it's likely to perform well in future predictions. If there's temporal trends, for example, you might find that you get a worse performance because you're not getting the temporal changes, or if there's a new variable that's introduced or removed, for example, if a variable is removed over time, then this might you might see a drop down in performance just because of that. And then you can say the split here. So 25 is the default setting, 75-25, but you can adjust that depending on how big your data are. And the number of folds used for cross-validation, the default is 3 to make it fast, but you can adjust that. So you could do anything greater than 2, or equal to 2. Then you've got the variable kind of selection. So now you can just do checkboxes of what variables you want. And they go through demographics, covariates, conditions, drugs, and then you've got procedures, measurements, and observations. For the conditions and the drugs, you can also use the vocabulary to group them. So the vocabulary actually does hierarchies. It says that this concept ID has children of these concept IDs. And you can actually utilize that by the children basically feed up to the parent code. You've got risk scores already predefined in here, so you can actually have the CHADS VAS, the CHADS 2, the Charlson, and the DCSI risk score already added. So these get calculated, and you can actually see if they're predictive in the model. The one setting that you have is like the minimum number of people that are required to have the variable for it to be included. So generally, because we've got so many concept IDs, if you don't set this, the chances are most of the concept IDs are going to be recorded for at least one person. So you're going to end up with a lot of concept IDs, but a lot of variables. But many of the variables are going to be very rare. They're not ever going to be in the model because they're just too infrequent. And even if they were in the model, they probably wouldn't be practically useful if it's very rare for people to have. So you can actually specify here a minimum number of people that have to have it recorded in their look-back period for it to be included and downloaded, and this will just save time. So normally this is set to 100, but obviously it depends on your target population. If your target population is smaller, you might want to reduce this down. And then you have the option of actually specifying, I only want to look at a certain set of concept IDs. So you can actually create a concept set in Atlas, and then you can open that up with the normal using this folder button here and say, I'm only interested in these concept IDs. And it will restrict your variable construction to those concept IDs. Alternatively, you can say, I don't want certain concepts included. So if there was some concepts that were used to define the cohort, you might not want them in your model. So you can actually exclude them from the variables. So this is the example for the CHADS2 variable setting. We're going to have our T of the atrial fibrillation, the O of the stroke. We're going to do a lasso logistic regression because the model they did was a score model, which is kind of closer to a linear model. We're going to, the lasso logistic regression actually has an automatic hyperparameter search because it only has one hyperparameter. It's easy to do that. You don't need to do a grid. Then we're looking at 0 to 1,000 days after the atrial fibrillation. We want them to have 365 days prior observation. We're going to include everyone. We're going to remove people if they're only partially observed after time at risk unless they had the stroke. And we're going to sample 10,000 just because we want it to be quick. We're going to do person split and 25% into test set, threefold cross-validation. In this case, because we're copying the CHADS 5, we only actually want the 5 variables. So we're going to add in age because that was a variable, and then we're going to say conditions in any time prior, but we're going to restrict to the variables that CHADS 2 mentioned. So we've created a concept set that has those. And then you can then go to, once you've created that, you save it, and then you can go to this tab here, which is Utilities. The Utility tab then opens up this page, and you can go to the R option here. And when you go to the R option, you then actually have all the R code required to actually do this model. So you can cut and paste this into R, press source, and your model will be generated, internally validated, and you'll get all the results out.
Question about that. Does it also create, the R code also create the cohorts?
No, so the cohorts will be created So the question was, does the R code create the cohorts? The cohorts you should generate in Atlas first, and then you'll be selecting them. So if you're using Atlas, you can only select cohorts that exist, but you do need to make sure you generate the cohorts. So when you're going to the cohort creation, there should be a generation tab, and you need to generate on the databases. If you don't generate, they'll never be created. So when you run this code, it will fail. So there are a little bit of editing in R that's required to run this code. So you need to actually put in the connection details. So this depends on the database you have. So you need the database management system, the server, the username, and the password to connect to your database. Once you've entered that in, you pretty want to make sure it works.
I have a question. Do you know anybody who has used this package with Impala? I know the connection script exists, but I don't know who those people are and have done it.
So if Database Connector works, this package will work.
Yeah, but do you know of anyone who has, in the community, or you're familiar with anyone who might have used that Impala connection? I know it's in the packet I asked Mark Tang yesterday, but I just don't know anyone else who's done it to help debug it. Okay. Blind leading the blind.
Peter?
Yes.
Thanks. So I was in the Common Data Model tutorial yesterday. How can Atlas work with OMOP, CDM, and generating cohorts? And, is there an interface? How can we maximize use of all these tools?
So the question is how to...
Well, if I want to start with the SQL programming, using the Common Data Model, I want to test things out. I can create a cohort with, or maybe I should ask, maybe I missed something yesterday. Can I create a cohort using the OMOP CDM and, let's say, a database that I've got, a Medicaid database? Then is there some way to transition, or is there some interface with Atlas? Or are they two separate?
So if you already have this, so Atlas works on any database in the Common Data Model format.
Okay.
So you need to have Atlas in the Common Data. You need to have your data in the CDM format, and then Atlas will run on that.
So that's the piece that I missed.
Right, so this is running directly on top of the data.
Okay, thank you. That's what I needed to know.
Okay, so then the next few bits you need to enter are the database schema that has your Common Database Model data. You put in the database schema that has the cohort. So generally, if you're using Atlas, this will be the same as your CDM, and then you have to add in your cohort table name, the outcome table name. Again, if you're using Atlas, this will just be cohort. If you're doing your CDM version, so 4 or 5, PLP actually only supports 5, so this should just be 5 at the moment. And then your output folder, so this is a directory on your local system where you're running the R code, and your PLP save name. So this is just something where you want, this is the folder name basically where everything's going to be output in the output folder. So you could name this whatever you wanted. Now the R functions, because I've kind of summarized how to run it in Atlas, but if you wanted to do it in R, then for each of these steps, this is how you do it. So I've assumed here that you're using Atlas, or you can just write SQL to create your cohorts. Then you've got create connection details for the database connection, create covariate settings to select which predictive variables you want, get PLP data, does the data extraction, create study population, create your study population. This is where the time at risk is defined. Set random forest or set any algorithm that we have is where you select the model and do the hyperparameter search settings. Run PLP trains the model, so it does the hyperparameters selection and the cross-validation. It does the internal validation, the test train split, so it trains on the test, trains on the train, applies to the test, and then it outputs all the different metrics, all the different plots, and some additional things that you'll see later on. And then the external validation, if you want to apply this model then to new data, it's just the apply model. And you put in the output from your run PLP in here, you put in your new data, your new population, and it will give you a prediction for the new population. So this, if you want to get some more insight into the R functions, then if you go to the Building Predictive Model PDF, it has extensive information about that. So just to kind of summarize some of the algorithms we've got. So I mentioned you could put set random forest. You've got set lasso lineage regression, set gradient boost machine, set random forest, set ADA boost, set decision trees, set multi-layer perception, set KNN, set naive Bayes. All of these work at the moment. So these are all the models you can pick. And then this table here just tells you the different hyperparameters. So how complex.
These are API calls. None of the memory comes into your laptop or what have you. So you're basically just feeding parameters in, and it runs on cloud. I don't need like memory.
You need it. So the data. So if you're using Atlas, generally the SQL will be kind of external, so it won't be on your system. So and the data, all of that. But when you're doing from get PLP data onwards, it's going to be extracting the data locally and then running everything.
Is there, so in say I wanted I'm curious about the memory constraints on this, like how much memory will be on, if I want all or like a broad set of
Okay.
memory, like will it blow up?
Yeah, so R obviously has the memory issues, but there is a package which we use, FFDF, and that actually doesn't do it in RAM. So you can actually extract large data sets and it still won't break it. So it would just probably be a bit slower because you've got bigger data. So any questions in terms of the information set?
So when you were restricting words to the 5 things which the chats used, you were referencing code set, and code sets in Atlas live specific to my idea. So inside my cohort, I define code sets, and I can find those code sets on their own. So if I'm using the Atlas option, I will have code sets which are not being used by my T or O outcome. I'm just confused. It seems to be that they get assigned some sort of, just like cohorts have their IDs, seems like the estimation and prediction now have their IDs. And is this the level where those code sets live?
So when you're creating your cohorts and you include the concept sets, then you can edit it locally to your cohort. But when you're creating the prediction model and you're accessing the cohort sets, that would be the general ones that you're then accessing. I don't think it'll be the one that's within your cohorts.
Okay, so the general ones on my Atlas server, or?
Yeah.
And can I just enumerate things in R myself? Or
You can edit, yeah, so this will just generate the R code and then you can make any edits you want. So there's a lot more flexibility if you edit it in R. You can change the time at risk settings slightly more in R, and you can. There's a few extra settings you can play around with.
And I have one more question, if I can, since no one else. At some point you said the first stroke, or one of the parameters was, do you want to consider further episodes of your outcome? So in the AFib problem and stroke, so let's say my first stroke was I'm starting at the year 2000, and I had a stroke in 2003 and another one in 2007. So I thought by defining my O cohort, I have to just narrow it down to like first stroke or all the strokes. So by nature, how I design my O cohort, it's either only the start and stop date of my first stroke and nothing after that. Does it mean that whenever I decide my O, I should not exclude any subsequent episodes of that outcome?
So with O, you can be very flexible. So we want ideally to create the cohorts such as O so that it's completely independent of your T and can be reused, for example, as a T for a different prediction problem. So when you're creating your cohorts, especially O, you can just say anyone who has a stroke. You don't have to put any restriction on first
all
time.
All their eras of
Yeah.
their strokes.
Yeah.
What if I clamp it down and by mistake, and I just says only consider the first? This will, even if I select yes, consider further strokes, because my cohort O definition doesn't include that,
then
it'll miss it.
yeah, so once you've extracted your data, it's only like on the extraction, it'll be using the dates. So you'd have to revise your O and extract the data again.
So this should be in the help file, like as you set up your O, just make sure you include all eras of the O and not just the first one.
Yeah, because if you said you're looking at a set time period for the O, and then you were saying, okay, actually now I want to exclude people who had it prior and stuff, then you're going to mess it up if you restrict the O to a set time or first exposure. So we've got 7 different things that come out when you do run PLP. You've got your input setting. So this is the information that, containing the settings you've put in, so what your predicted variables were, what your time at risk settings were, the minimum prior observation, the cohort IDs, and all this sort of stuff. So this is all here. So you've got reproducibility, and we use this to actually apply the model in the future. You've got your execution summaries. This tells you information about the computer that was used to do the model, the R version, and the PLP package version. So again, this is just for tracking. You get the actual model. So this is what you're going to be using to do the prediction on the new data. You have your prediction. So when you're doing the validation, you've got your target population. This is actually the prediction for all of those target people. So this is the internal validation. You obviously have to apply the model to other data to get your external validation. Covariate summary is just the patient characteristics. So and it's split up to the test set, the train set, people with the outcome, people without the outcome. So you've got a lot of different information about each of the variables there. So an example of the covariate is this. So you have a covariate ID in your data that corresponds to the covariate name, which tells you what it actually is. So covariate ID of 23 was the age group. One of the age groups, you have analysis ID, so this tells you whether it's demographics, conditions, and the time period. You have the actual covariate value, and this is actually the value of the kind of the importance in the model. And then you have the covariate counts. This is how many people in your target population had it, and you have your covariate count without the outcome, with the outcome, and so on. So this is a large file. This will get saved as a CSV when you run the model. You also get a scatter plot, and there's an interactive scatter plot as well when you use the Shiny app for viewing this. So you can look at how common it was in the people who didn't have the outcome versus how common it was in the people who had the outcome. So anything above the X equals Y means it was more common in people who had the outcome. Anything less means, lower the X equals Y means it was more common in people who didn't have the outcome. So this gives you information, and sometimes you can scale this and color it depending on the covariate count or the covariate value and so on. You also get a plot to see whether your test train split was good. So you have the train set mean and your test mean for the outcome and no outcome to see if the variables were distributed well equally across the test and train set. So in this case, we see it's actually on the X equals Y line, so that's nice. The test train split was good. If this was, if you had a small data set, you're more likely to have this away from the X equals Y line, and then you probably want to repeat your internal validation a few times because you're more likely to get performance that might be optimistic or lower than it should be. Then the analysis ref just tells you some information like the analysis ID. This isn't really too useful, but if you're going to be inputting or uploading your data into your results into a table, then you might want to have some analysis ID so you can refer to that in the future. So performance evaluation is the main output that you're going to be looking at once you've got your results. And that contains information about your calibration, some information for doing the ROC plot, some information about the demographic calibration, information about your prediction distributions, and just some summaries about the area of the curve and the calibration and so on. So the calibration summary, what that does is, say you've got 10% of the patients are going to experience the outcome, so this is your group of people. We're actually going to order those based on their risk. So people with the largest risk are going to be in the top left-hand corner. So this top person here, when you applied the model, this person had the highest risk given to them. People in red are the outcomes, black are the non-outcomes. So then second largest risk is this person, 10th largest risk is this person, 100th largest risk is this person. And we keep on doing that all the way down to the lowest ranked person. So this person had the lowest risk assigned to them by the model. And when we do the calibration, we then partition this up into 10 different groups. So we look at this group is the top 10% risk people, this is the next risk group, and this is the lowest 10% risk people. So when you're doing the calibration within each group, then you calculate, okay, in this group, 38% of the people had the outcome. And then you also calculate the average risk for these group, which was greater than 42%. So that gives you a point on your calibration plot. And you do this again for every single group. So in the bottom group, only 3% of people had the outcome. And you'd calculate the average predicted risk. So then you end up with a summary or a table that basically says for each prediction threshold, you have the people in that group, you have the number of people that have the outcome in that group, and then you have the average predicted probability. So you're going to be comparing the observed probability, which is people with the outcome, divided by the person count, with the actual average predicted probability. You have that for 10 different groups, which gives you 10 different points on your calibration plot. So each of these points here corresponds to one of the risk groups. And then you've got the average predicted probability and observed predicted probability. If it's a well-calibrated model, then the average should match the observed, so you should get all the points along this x equals y line. And in this case, we actually did have a nice calibration.
Still having a little difficulty understanding the calibration concept. Is this one way of validating your results, or you're going to change something in your methods based on what you get from your calibration process?
So I would say the calibration is there just so that the risk that the model's assigning you, you want it to be your true risk. So if the model said that, so if the calibration was off over here somewhere for some of the people, then that's saying that the risk the model's assigning you isn't your true risk. So if you were just to tell people you're going to have the outcome, so if we're going to put a binary kind of threshold and say, okay, anyone with a higher risk than 50%, we're going to tell have the outcome, and they don't, then the calibration maybe isn't so important as long as the 50%, as long as they are given greater than 50% from most of the people. But if you're actually going to tell them their actual risk, you want that to be as accurate as possible. So the calibration is just to make sure, is the risk that the models have given you true, or is it an overestimate or underestimate? We need to know that because you might want to recalibrate your model if it's wrong. So
how would you recalibrate?
So we don't actually have this in the package, and I'm not quite sure what process people go through with that. My guess would be that if you knew the underlying prevalence, then you could use the ranking, assuming that you've got a true representation in your population. You could use some rank and say, okay, we know 10% of people have it, so maybe we'd expect these 10% of people to have a very high risk, or do something with like some sort of thresholds. But it's just, I mean, when I'm doing models, I don't generally look at the calibration. I look more at the discrimination, because if it's able to discriminate, then you can recalibrate probably. But it's just there. So
I think just a very simple example, though, is when you use a predicted probability, if you were told you have a 10% chance of something happening to you, you'd like to know that when you're told 10%, that in fact it's going to happen 1 in 10. And so what calibration could tell you is you got a predicted probability of 10%, but maybe your actual risk is 20%. In which case recalibration would say, every time I see 10%, let's figure out a way to make it say 20. And so calibration is first just asking the question, when I give you a prediction, is it in fact what you're going to observe? And if that's wrong, then there are procedures that you can apply to basically correct for how off you were. What we like to see, like what Jenna showed here, is you'd hope that you're just not off in the first place. Then you don't have to fix it. However, if you learn that you're off, there are procedures that you could apply to correct whatever error you're off by.
Generally, the recalibration occurs more when you're applying it to new populations. So generally, when you fit a model, people don't often recalibrate. But when they're applying it to a new population, then you have to do the recalibration.
I think the misunderstanding is that many people use the word calibration as fixing a deviation from the expected result. This is just observing whether or not there's a deviation from the expected result. That's it. And then what Jenna and friends call recalibration is to add some extra finesse to now put it back to where it should be. I got first into the same misunderstanding.
So if I may also ask, is that standard practice in reporting on the model that you bin it in those bins by just the things you observe? I mean, what if I want to bin it by 0 to 10% risk, 10 to 20, and I just don't have anyone in these bins? So it seems to me rather arbitrary. Why 10 bins? Why not 15? And so on.
It's a great question. So we actually do it in 10% of the highest risk. So we don't actually say 0 to 10, 20% risk.
I
we
know,
don't,
that's exactly what I'm pointing to. Why not other way, and why not 15 bins?
So the reason we don't do the reason we don't partition 0 to 100% probability up to 10, because a lot of the time you won't have a risk greater than 5. So if you did that, you'd only really end up with 1 dot. So this is the way just to get the 10 dots. But it is kind of the calibration and the plot you get really does depend on how many partitions you do. So if you did 100 groups, you might end up with something that looks very off for some of them. 10 just tends to be the standard that people do. And then you might often see that the high risk group is off quite a bit.
So if I go into literature and read some excellent papers following all the criteria, I will see plots like that?
Yeah, pretty much everyone does 10 dots in the literature.
Okay.
But it's just because we've got a binary outcome, we have to group to get a non-binary value for the y, and then it's arbitrary what you pick, and that's why as well it's good to inspect it rather than do any sort of best fitted line and stuff, because any outlier could affect that. So
in general, the methods that are strong at just baseline classification are not necessarily very good at giving calibrated probabilities in the output. So you may typically want to use something like isotonic regression, or there's a whole class of methods, things like that, to calibrate your probabilities that you get out. So if you just apply baseline logistic regression, for example, the probabilities are usually not well calibrated. That's okay.
So the threshold summary, this is used,
in your experience, how you seem that you're picking groups in order to calculate that average observations, that outcome observations that you found. In your experience, how changing those grouping actually affects the calibration?
So if you're doing a visual inspection, I don't think it's not too much of an impact. So if you say you wanted 50 points and you had enough data to do that, then you might see 1 or 2 points off if it's a small kind of group, or because you're going to have less confidence in that group. But if you're inspecting it, then you're just going to see that and probably not be too bothered. If you're trying to do like a line of best fit like this one does here in this plot, then you might find that gets affected by the outlier. Which is why I tend to not look at the gradient and the intercept when I'm doing this. I look at the picture and see whether the dots fall along the x equals y line. But at the moment, I personally don't think there's a good metric for summarizing the calibration. And even the plot isn't really ideal all the time, and it's arbitrary how many points you put. So I mean, there is actually some metric that will summarize the calibration, but it's sensitive to big data sets, so it looks at the significance. And if you've got a big data set, everything significantly deviates. So it's always significant on our data, so we don't use that. So the calibration is always, you just generally look at it and just get a feel for it. This is what I tend to do. So the threshold summary is what we use for doing the ROC plot. So it summarizes your sensitivity, specificity, and various other metrics at 100 different points. So you've got a sparse savings of it, and you can redo the plot rather than if you've got big data, it could be quite a big file. So the way that's done is that, again, we ordered people by so the reds are the people with the outcome, the black people without the outcome, we ordered them by their risk, highest at the top left, lowest at the bottom right. Then we can pick at different thresholds. So here, for example, if we picked a threshold of 0.65, we'd find that 10 people would the outcome, and 990 were predicted to not have the outcome. So this gives us different true positives, true negatives, false positives, false negatives, and so on. So we end up with a plot like with our plot true positive, false negative, true negative table. And for that, we can calculate the various metrics like the positive predictive value, sensitivity, specificity, accuracy, F1 score. And then we might want to do that at a different threshold. So, for example, we could pick the threshold at 0.27. We would get a different table here. And then if we do this for 100 different points and calculate all these metrics for 100 different points, we end up with our threshold summary table. So this is telling us our prediction threshold along here that we're using to look at people above or below to say whether they're going to have the outcome or not. We also normalize this with a preference threshold because this can give you a bit nicer plot sometimes. Then you get your positive counts, your negative counts, your true count, your false count, true positive, false positive, true. You got false positive, true negative, false negative, sensitivity, specificity, and all the different metrics all in this table. So this is another one you can look at to see how the model's doing it at 100 different points. And this will be used to create your ROC plot when you call that function. And then here's just like a summary to tell you how good a ROC plot is. I'm sure many of you have seen this quite a lot. So ROC plot that kind of goes up quite rapidly along this line is a good ROC plot. It's almost perfect discrimination. A ROC curve that kind of goes near the x equals y line is terrible. It's random guessing. So you haven't learned anything. Then you have your demographic summary. So this is going to be a calibration, but a calibration for different age and gender groups. So now we're going to have the outcome and non-outcomes. We're going to separate them by the age and gender. And then within each age and gender group, we can calculate the average compared to the observed. And then that will give us a table where it says our age and gender groups, so male age group, and then it tells you the people who at risk and the outcome, so you can calculate your observed risk, and it's got your average predicted. Sometimes you don't have all age and genders, so you've got NAs in there, so it depends on the population. And you get a plot that looks like this. So your age is along here, you have females up here this side, males this side, and then your observed fraction here. So you've got the observed and expected, it plotted in blue and red, and if these lines fall on top of each other, then you've got it nicely calibrated across age and gender groups. In the last one here, I'm not sure what happened, the red, so the observed was much higher than the expected, so this age group seems a bit problematic in both of these plots. Then you have your prediction distribution, so this is just the, you look at the high risk to the low risk probabilities, and you look at how dense they were for the people with the outcome without the outcome, and then you just have a summary basically that says for class 0 is people without the outcome, class 1 is people with the outcome. You have their average predicted probability, standard deviation, the min, the fifth quartile, and it goes on, so you just got some summary of the distributions of the predicted probability for people with the outcome and without the outcome. And that can generate a plot like this. So you can see this is what Peter showed right at the beginning when he was showing this interacting with what a ROC plot looks like. So if these are very separated, so if the blue and the red plots are very separate, then we've got a very good discrimination, your model's working perfect. If you've got overlap, then it means you're not able to discriminate quite so well.
Is there any guidance around how many events there need to be for the model not to be overfitting? Because I know especially the Odyssey, we are using all the variables in the model. I mean, like in the data set. So, I mean, is there is just like we do sample size power calculations sometimes? Is there something similar for this?
So we do actually have built into the package, you have to have a minimum number of outcomes. I think it was around 20 or so. That's just an arbitrary value. I think if you have less than 20, you're probably not going to be able to do models. But in general, you can tell if you've overfit from the test and the train performance. So if you're getting a really high performance in your train set and very low on the test set, then that would suggest that you're overfitting. So I think you'd be more inspecting your model to see if you're overfitting rather than not doing the model if you have a set number of outcomes.
Okay, I thought the 20 was that each concept had to be available in at least 20 patients. I didn't realize that was the outcome that we needed to have 20 outcome events?
So this is a different thing. So the setting for the minimum number of people needed for the variable is different from the number of outcomes. So when you're running the model, the PLP package just checks, do you have at least X amount of outcomes? And I think the threshold is 20, and if it's got less than 20, it just says not enough outcomes. Greater than that, it will try to train the model. But if you've got a low number of outcomes, you might not be able to train a model, so your performance might be poor. Or you might, for example, the logistic regression might not converge, and so on. So you might end up with issues. But and as people said, if you have a low number of outcomes, also the metrics can be difficult to interpret, because even if you have a high end of the curve, it might not be useful as a model because you're still going to have a very high false positive rate, probably.
One suggestion I would have is to look at learning curves. Basically, you reduce the training set size and keep adding some additional data and see and do this randomly over a few shufflings, and you will see that your AUC will start flattening out after a while. So that will give you an indication of whether you have enough data or not.
Yeah, and actually that's what we already did. So the poster that I was presenting yesterday does actually that. So we look at how many outcomes we actually need to do a good prediction. And the question is, do we really need these big data sets for these type of prediction problems? And it turns out that after like 4,000 or 5,000 people with the outcome, it just flattens out. You don't need to run bigger data. It doesn't help.
And then another way of visualizing this, just a summary, is just a box plot. So this is what a lot of papers will put into, prediction model papers will put in. They tend to go for the box plot rather than this sort of distribution. And you can just see if you've got the outcome people and non-outcome people being quite separated, and these lines quite far apart from each other, then you generally got a good model. And then the final thing is just the evaluation statistics. This is just a summary. This is pretty what I use the most. So this just tells you for your train set and for your test set, for various metrics, what was the value. So you've got your population size, number of people who had the outcome in your train set. You've also got that for your test set. Then you've got your area under the curve for your train set, area under the curve for your test set. So you can see here the performance is pretty similar, so you haven't really overfit. Then you've got the Bria score, which just is the squared difference. Not generally that useful. You won't generally use that much. And then the calibration, intercept, and gradient. So we do the line that fits to the 10 different points to give you a summary. But as I said, I think it's better to inspect the plot than rely on that, because it can be affected quite a bit by a general outlier. So, any questions?
Where does it fall?
So the folds are for the hyperparameter selection. So once you've found your hyperparameters, then you'll do the model on all the training set and apply it. So once you found your hyperparameters, you then find your parameters on the training data. So you won't have the fold information here, but there is a table in your model that says for each hyperparameter setting what was the performance, so you can see what the final model selection was for the hyperparameters.
Real quick, how do you get the confidence intervals for the AUC? Is that a bootstrap?
So that's done with Martijn created area under the curve calculator for that. It's only done if you have small data. So generally if you have big data, we don't even bother calculating because it's taking a long time. I'm not quite sure what implementation he used to generate. I can find out and let you know.